result point of view, it's not the true. So even though I give the 4 choices, so random guess is around the 25%. The correction ratio is less than 50%. Really, I tried my best to make the choice easy and obvious, but I don't know how much you are serious for the multiple choice. So please read carefully and answer best one. So that is the multiple choice. So mostly straightforward question. It's not the calculation. It's mostly easy definition or the selection. One of the correct one or the non-correct one from the list of the calculations or definition is probably easy. The other 70% for the probably 5 to 6 question, open-ended question. Okay, I'm not going to ask you directly code something algorithm or whatever, but the reverse way, which means you should be able to understand the code itself to answer the question. Okay. So probably I'm going to use some skeleton program or the simple code of the Java or the C to make the question of the something algorithm. Okay. So you don't have to memorize the code itself. Instead, I strongly suggest to understand the algorithm. So if you have the basic knowledge of the program, any program type, so sometimes my question in the question, my programming code sometimes not very correct in terms of syntax, but the main part of that such a question is whether you guys understand the algorithm or not. Okay, so which means at least you should be able to understand the code itself. So you don't have to study separately for the programming code. Instead, try to understand and apply. Should be able to apply the algorithm. We covered those. Many algorithms from chapter 3 to the 6. So 7 will not be part of the midterm exam, it will be part of the final exam. So that's the mostly probably that you can focus on. And some of the open-ended question is just a list of the advantage or characteristic, or some of the question asks the calculation of the something evaluation or whatever. Also, it will ask about the algorithm itself. Any question regarding to the midterm exam? Or the distance run, the online course student should attend the on-campus exam. I'm not going to allow any remote exam. If the only exception is remote, the online degree student. Okay, there are few students who are taking this course from the distance as a distance learning degree student. So they can take the remote exam. The other students should be in the campus, the classroom. Yes.
Will the midterm exam have some definition questions?
I'm not going to directly ask what's the definition of operating system, something like that. Probably will be part of the what is the multiple choice. But in open-ended question, it's not directly asked write down the definition of operating system, but not like that.
So there's
more comprehensive question.
So there's no questions like what is kernel mode, what is user mode.
But definitely you should understand what is the definition of that to answer the other questions at open-ended as well as multiple choices. But I'm not going to answer such a directly like your quiz one. So I don't ask such a simple definition. Also, if you, I'm not going to allow any cheating sheet. It's plausible. So, but I understand I'm not very good at memorize everything. But first thing is understand the concept of the operating system algorithm and contents in the textbook. Then next thing is if you cannot understand, but sometimes even though you understand, if you cannot memorize, it's nothing. So it should be balanced. Okay, any other question? The difficulty level, usually I focus on the average level, around 80. Lower 80 is average. So that's usually when I make the exam, I focus on. So average means it's around B or the sometimes B plus if you all the overall performance is good. But if overall performance is not good, it's usually B minus. So it's B minus to B plus range is gonna be the average of this class. So usually I focus target on the 80, but usually works. Regarding to for the undergraduate student, so it's the same question, same exam, and same activity, but when I decide the final grade, it will be separated. Okay, don't worry about the such a difficulty level. I already mentioned. Any other question? Okay, so the most important the material of this exam is not the PPT file, it's a textbook definitely. Okay, as I mentioned at the beginning of the class, that this is just supporting material for the convenience during the lecture. Okay, so it may be possible there are questions which is not mentioned directly in the slide, but if I mention during the lecture, so also it's a part of the textbook, definitely it will be. So the textbook is the first material that you can study for your midterm and final exam, including the exercise. One of the good thing of this textbook, the dinosaur textbook, is it has very nice exercise as well as the lab. So it's good for your understanding. Okay, before we start the deadlock, so we didn't finish the scheduling algorithm. Also in the scheduling algorithm, so last class I introduced the multi-level feedback queue, which should be implemented in your project. So first thing, you need to understand what is a multi-level feedback queue, and also you should know how it works. Also, it will be part of your midterm exam also. So yes. So this is an example of the multi-level queue, exactly same the condition as you are going to implement in your project. So we have the three different queues. First one is a quantum round robin with a quantum size 8, and the next one is a quantum size 16, and last one is a first come first serve. So the main advantage of using such a multi-level feedback queue is if you have the process with the short period of the CPU burst time, which means it's a short amount of the CPU burst time, it will be processed at the first queue. If not, which means it's longer than the A CPU burst time, it's moving to the next. Eventually, it will be processed with the first come first serve. Also, you need to consider the scheduling along the queue. We have the 3 queue. So in this example, we are going to use a priority-based scheduling for the queue, which means if there exists any process in the first queue, round robin quantum A, so it will get the CPU resource. Then apply the round robin CPU scheduling algorithm. If in case empty, then you can assign your CPU time to the second queue, and so on, the last one. So which means whenever you have any incoming the process, the new process in the ready queue, it will get the CPU resource. Then which means it provides fast response time. Also because of the first come first serve, eventually it will be processed. real-time CPU scheduling. So rate monitoring scheduling is we are going to consider different priority for the process. That is the each process has the target deadline. Okay, that is the real-time processing. Real-time does not mean just the fast processing. Instead, real-time processing means it's a guaranteed time. So, such as the smoke alarm system or the nuclear plant, the warning system. So, within a given time or assigned time, predetermined time, the process or the job should be completed or the first response that is the real time. So in this case, we are going to consider the shorter period of the CPU burst time is a higher priority. Usually the in the first remaining job first algorithm was the shortest remaining job first was the shortest job first. So consider the small amount of CPU time should be processed. Otherwise, it will be hidden by. So because of the due to the conveyor effect, the shorter job will be hidden by the longer job. Okay, so that is the idea of this one. Then, using such a period time, we can assign the CPU time. And also another way of the real-time CPU scheduling is always that deadline first scheduling, which means the process 1 has the certain CPU burst time, but it has a target on the 50, but if that is not completed, so what is the remaining time to the deadline? So which means if such a the deadline, the current time to the deadline is the shortest one, we consider such a process is urgent to be processed. So these kind of processing are soft to real-time processing, which means we try to target on finish on time, which means before deadline we try to complete the process, but sometimes we cannot complete such a process, so that is a soft deadline. So this is also soft deadline. So we give the higher priority to the earlier the deadline, otherwise the lower priority. Okay. And also proportional share scheduling is the we consider amount of the remaining time. So based on that we prorate. Okay, give the priority, not just give all the priority. It's kind of preemption version of the earliest deadline. That's the idea of the real-time processing. You can go over the example of the scheduling in the Linux and the Windows. Probably the Windows client press you already know, such as 7 different the priority, real time, very high, high, very high, the normal, slow, something like that. It's the same idea as the priority 0 to 15. Right here. The time critical, highest above normal, normal, below normal, goes the either. Either is nothing. One more thing. So after we develop the new algorithm for the CPU scheduling, we'd like to evaluate whether the algorithm really works better than the other. Then there are different ways of analyzing, evaluating such a CPU scheduling algorithm that include the deterministic modeling and queuing model. Third one is a measurement from the implementation, and last one is the implementation. First, the implementation means you implement operating system with your new scheduling algorithm. Benefit is correct. You can easily realize whether the scheduling works better than the other or not. The problem, it requires a lot of time and the workload, and also what if that doesn't work very well? You need to go back. You need to start from the beginning. So this the implementation, real implementation, is not used a lot after you verify. Okay. the algorithm using the other method, evaluate the, your algorithm the other method, then you can apply to the real operating system. First one is deterministic modeling. Deterministic modeling is given just like what we did in the first come first serve, or the shortest job first, and other scheduling algorithm. We use something process state. Given CPU at the process information and the burst time, we evaluate. It's a deterministic. Okay, so that is the one of the way to evaluate the algorithm. The benefit, we can decide clearly which one is better than the other, right? The problem, it's not possible actually to get such a CPU burst time in real life. Real implementation, can you guess how long it takes your MS Word program, or the sometimes even though you execute the create the process, exactly same process, but takes sometimes longer time than usual. Sometimes it's faster than usual. You don't know exactly what is the required CPU burst time. Okay, so that is the problem. However, still it's a good method, and also it's very cheap. You don't need. You can just calculate even such a CPU burst time using the deterministic modeling. The next one is because on the other hand, so we can model such an incoming process as the statistical approach. Okay, so I think that if you are taking the statistical course or the some network the course, you use the queuing model to model incoming the network packet. In other words, so if you are taking the statistical course, so if you go to the McDonald's or retail store, so can you model the period time between the one customer and next customer? How? Sometimes the two customers are coming the almost the same time, but sometimes you have the time between the two customers. Based on that, you can model incoming customer, then assign the sometimes the 2 register or the 3 register. Sometimes if where the incoming customer is not frequently, then you can assign only 1 customer. That is based on the queuing model. How we are going to model, we are going to consider incoming the customer in the queue. Okay, how many queues are in the queue? Then if it's too long, then assign more. If it's short, assign the less, the register. Okay, then mostly such a queuing model will be the exponential. And another benefit of such a queuing model, the exponential queuing model, is you can use, you need only one parameter, that is the mean value. What other statistical model have you ever used or heard? Gaussian model. Gaussian model is a normal distribution. Normal distribution, you need mean value and variance. Okay? For example, Gaussian model, you need the mean value and the variance. So, but incoming, such an incoming customer or incoming packet, so in creating the process, can be modeled by such an exponential. So using that exponential, you can model, or you can evaluate your scheduling algorithm. At the time, we can apply the Litter's formula. Litter's formula, nothing but the if you have the longer queue in this, so for example, so when you have the longer the queue, which means arrival time is short because it has more incoming the packet or creating more process or the incoming the customer, which means you need longer waiting time. So that can be like the lambda is the average arrival ratio. It's a small means the small value of the lambda means okay, so you have longer the queue, and the W is the average waiting time. So if you have the longer queue, your average waiting time will be increased. So that is the Little's law. So using Little's law, you can guess the predict the average waiting time of your scheduling algorithm. That is based on the statistical approach. Okay. So queuing theory also used for a lot in computer science, especially for network model. So network model, how you process. So incoming, for example, web service request is not follow the Gaussian distribution or the uniform distribution. Usually it follow exponential distribution. So then you can model guess how many web service we need or network bandwidth. So you can decide such a thing. Simulation is instead of implementing the real operating system or real computing architecture, you can use the simulator that simulate your operating system as well as the computing environment. For example, one of the example of such a simulator is when you are doing the Android programming, you don't need the real device, right? You can use the emulator. It's exactly the same idea. At that time, if you have the scheduling algorithm, you can replace the current scheduling algorithm by the yours, then run your emulator. That is the simulation. Okay? So simulation used a lot nowadays. Instead of the real implementation, it costs a lot, high cost. But in specific case, like the nuclear, the smoke detector in the nuclear, the plant is very, very critical, right? At the time, you'd better test your device with the real implementation. Okay, I think that this is the last chapter, last topic of the process management. So far we have discussed about the creating process management. So we define the data structure of the process in the chapter 3. Then in case we need the more performance or the similar job of the process, we can consider thread. The thread share the sum of the information in the data structure, process data structure. Then it's not the independent process, but it's kind of the clone of the process. But you can create the parallel. You can do the parallel processing using the thread. That is a multi-thread programming. So in chapter 4, and also we have discussed about the process synchronization because we are doing the in current operating system, there exists more than one the process. They are accessing, sharing the same data. It's a shared data at the time. There might be the race condition. Race condition, when you have the two processes about they direct access the same data, we cannot guarantee the consistency of the shared data. So to address that problem, we can consider the critical section problem. We can define such a synchronization problem as the critical section problem, which means whenever the process access the critical section shared data, we define this is the critical section. But when you enter such a critical section, you need to get the permission. So we can implement such a synchronization problem as the basically lock and unlock. So you need to get the lock to access key to access the critical section. Then when you leave such a critical section, then you can release such a lock. So there are different solutions in the synchronization problem. You can use the software, which means you can use your own algorithm, okay, to solve the problem of the synchronization critical section problem. Another solution is the operating system solution. Operating system provides some data structure, okay, such as the semaphore or the other. So you can use such a thing as a log. For example, the mutex. Mutex is a binary semaphore. It has 0 or 1, so we can consider. So the wait is the locking, and the signal is the release the lock. So we can use such a thing. Similarly, we can use the hardware solution. Hardware solution means we are going to use instruction level. Instruction is atomic level. Okay, so we can implement test and set or the swap the instruction, because it's it cannot be divided into two. We cannot be stopped once that instruction is started. So we can use such a hardware solution. That is a synchronization problem. And also, last week we have talked about the scheduling. When we have the multiple processes, they drive to access the limited CPU resources. Especially the CPU resource is the most critical resource in the in our computing architecture. Also, the operating system should consider seriously how to share such a limited resource. Even though you have the multi-core, it's just nothing but the 2 core. So at the same time, ideally it can process 2 threads of the instruction. But how many processes you have in your operating system? It's just so many, sometimes more than 100 need to share such a limited CPU resource. So to address such a problem, we can consider basically most of the CPU scheduling algorithms are based on what? Priority. In first come first serve, arrival time is a priority. So first arrive process, which means the most highest priority will be selected as a dispatcher, then we'll get the CPU resource. Another example is the shortest job first and shortest the remainder job first, and also priority based. All of them can be two versions of that CPU scheduling algorithm. One is preemptive, another one is non-preemptive. Preemptive means the non-preemptive means once it starts, it will be completed. Okay. On the other hand, the non-preemptive, preemptive means it can be stopped in the middle. Then the CPU scheduling will select one of the processors from the ready queue. So when you solve the problem of such a scheduling algorithm, I strongly suggest to use Gantt chart, your ready queue, and the terminate queue. So we learned about the 5 the process state, the new, ready, running, wait, and terminate. You need to follow such a thing. Okay? Then finally you can evaluate your scheduling algorithm using waiting time, average waiting time, average response time, average the turnaround time, and average the number of throughput, that process, and so on. Okay. Also, there are different ways of the evaluation. That is one way. So we use the deterministic evaluation, deterministic modeling for the evaluation of the scheduling. Also, you can use the queuing theory. It's a statistical approach, and the third one is the simulation. And finally, you can implement to test your CPU scheduling algorithm. The last topic is, because the modern operating system support multi-programming. Okay, so multi-programming means you have the multiple job, multiple processes. Then, simply, there are two. One of the examples of such a thing is, so this is the bridge. This is from west to east, and this is east to west. Okay, there is a train running this one. There's another train running this one. Fortunately, they are double line. One is going to this way, another one this one. Going to this way, one other way. There's no problem until they meet each other and on the bridge. Unfortunately, this bridge has only one lane. Okay. Then, what can be the solution?
Traffic lights.
Traffic light.
If one train's on the
So
bridge.
one of the easiest way is we can explode one of the train. I mean, yeah, that can be solution. Then we can go the other way. That's really happen in operating system. Or we can this one, Also, another way is it's not easy in the train. You can back up, okay? Then wait, then going this one. So this is another solution, okay? And it's not easy, but you can solve this problem by constructing, building another bridge, right? So there might be different ways. This is exactly the same problem in the operating system, okay? But this is true. The deadlock can happen anywhere, not only in the operating system but also in our daily life. So, for example, when I see my daughter and son, they usually keep fighting because they don't want to share the item or the something to eat or the toys. They never want to share their item. Then they want to get the new one whenever. If I buy, so that is the reason many parents actually buy two things or multiple items. So it can be happen. The solution might be similar. So we will formalize such a solution, how to solve such a deadlock problem. So first we are going to define what is a deadlock in operating system in terms of process, and what is the categories of the solution. There are different ways of the solution. First one is operating system never allowed to enter deadlock situation, which means prevent, okay? Also, another way is you'd like to avoid. So you will process your process state, but you'd like to avoid such a deadlock. Prevent and deadlock is a little bit different. It looks like the similar, but prevention means you are not going to enter such a next stage, okay, until you solve the problem of the deadlock. So prevent. But avoid means you progress your operating system state, but you try to avoid, okay, that around such a deadlock situation. That is the first way, prevent or avoid. The second is you don't care first time, enter if something event like the creating the process or the requesting another resource, then you need to check whether this may cause deadlock or not. Okay, you need to check. That is the second solution. Third one is you ignore it. No matter what happened, you enter the next progress, your operating system. Then, what if there is a deadlock situation? Application program or user will be in charge of such a thing. Why? Because the first two solutions are very expensive. If operating system check, for example, I have the 50 students, so they keep fighting each other sometimes. So she wanna his the homework and he's waiting for another student one. Do I need to check all of this? No, I don't know. So you guys be in charge of such a problem because you are the not teenagers, they're almost the trained and growing up. So you will be in charge of that. That is the reason when you are using operating system computer, even though you are using the fancy nice very nice operating system, you may encounter such a deadlock situation. At that time, the solution turn off and turn it on again, or the Control C, or the terminate your program. So that is the general things. Then, what is the deadlock? It's just simple. You have two processes. They are holding resource like the, for example, CPU one. This one is holding memory. And this process one request this. At the same time, process 2 is request this resource. Can we move to the next step? No. Until we solve the problem, they are keep waiting. They are fighting to get another resource, which is held by another process. This is a deadlock situation at this time. Okay. The resource, this one. Process, we have discussed a lot. The process. Resource means it's any kind of resource in computer. Okay, it can be file, it can be even data structure, file structure. Okay, it doesn't have to be physical resource. It can be operating system resource. Okay, it can be CPU resource, hard disk drive, and memory. Also, in addition to that, the operating system structure or application programming structure, data structure, file descriptor, header, all of them can be considered as a resource. For example, even semaphore. So we can use the semaphore for the to solve the problem of the the synchronization. Okay, at that time to acquire the lock, we can use the wait. So wait. So we suppose that we have the two semaphore. So wait A means the process 0 apply the lock of the semaphore A. At the same time P1 get the lock of the semaphore B. Then what if the process 0 request the semaphore B, at the same time P1 requests the semaphore A. They are keep waiting. So that is a deadlock situation. See? Like the bridge crossing example. It's a real actually example mentioned in the textbook. So this to solve the bridge crossing the deadlock problem, we can think about the several solutions, like the backup or the one each other, something like that. Another example is if you go to Manhattan, you may encounter such a situation. The solution: yelling each other. Back of your car. This is a car. So it really happened. Especially when before I moved to United States, I was in the Seoul, one of the highest population in Asia. So I think that it has nowadays 11 millions in a city. It's a small city. So actually this is a Seoul, and I lived in the outside of the Seoul. It's a satellite city, but my office was just crossing the Seoul, so it took 2.5 hours to drive. Sometimes I going around the bit, one takes the 3 hours. So at the time I encountered such a situation a lot. So one of the solutions is the policeman should block one of the one and back up such a way. Same thing in there. We can consider this is a series of instructions and this is a resource. Okay? The crossing is a resource and this is another process and crossing is the resource and how can we solve such a deadlock situation. So first we need to model the system, computer system. So R indicates the resource type. So we have R1, R2, R3, Rn. So we can consider CPU, memory, I/O device, any computer resource as one of the R1, R2, R3, something like that. And each resource may have the multiple instances. For example, I have the disk 0, disk 1, disk 2. Such a number of the hardware those resources are considered as the instance. So for example, Ri has the Wi instances, which means for example, if we consider Ri as the hard disk drive, when you have the two hard disk drive, two disk controller, then we have the two instances. That is an instance. Then to acquire the resource, in other words, to utilize the resource, you can use their own method or the system library, system code like the request, open file, or allocate the memory. It depends on. But we will consider all of these action as a request to get the resource and to release after you use. You can release such a resource utilization. It can be different in the real implementation, like you can release the lock or you can close the file, you can free the memory, but we will consider all of this action as the release. Okay. Then also we have the process, so which means we will use the P1, P2, and Pn number of process in our system model. Then what is the deadlock? So deadlock is the multiple process are holding the resource, computer resource, and request the other. Okay. Then after we investigate the deadlock situation, we characterize the deadlock. They can be summarized as the four things. First one is a mutual exclusion. Okay. So first one is a mutual exclusion. First one is when you have the computer resource, it can be used by only one process. If you allow the multiple process to access the same resource, there might be no problem in terms of deadlock, right? So for example, if this one can be accessed by the multiple process, then this one can get the usage of the disk, then it will be completed, and the process one can access. There's no problem on the deadlock. However, if you allow only one process to access the computing resource, that is the mutual exclusion. So to be a deadlock situation, all resource should be mutual exclusion. Then hold and wait. A process is currently holding. The process that caused the deadlock situation should hold the computer resource R. Okay? Then need to request another one. If this process does not request, okay, then they may not cause any problem. This is just heading. Okay? Then in case the process hold and wait, that causes the deadlock situation. The third characteristic of the deadlock is no preemption. No preemption means, what does that mean? Preemptive and non-preemptive. Preemptive means it can be resumable. You can stop and back up, then start, resume later. So non-preemptive. The preemptive process means it can be back up, stop, and release the disk resource, then start again. That is preemptive process. Non-preemptive means it's a should wait. They don't want to go back. Okay? Keep the current resource, then keep waiting for next resource. That is a non-preemptive. So non-preemptive case, so you may cause the deadlock situation. The last one is the most important. Even though the mutual exclusion and hold and wait no preemptive, if the process, this one requests this one, but process 2 requests the other, process 3 and hold, process 4, if in that case there's no problem, okay, in terms of the deadlock. It can be completed, eventually it will be completed. So any case in the deadlock situation, you can find something circular way, okay? That is the most important one when you find the deadlock situation. In even two process case is a circular way. They wait each other. When you have a multiple, you can find such a circular way. So as you can see here, process 0 is waiting the resource held by the P1, and P1 is held by P2, Pn-1 is waiting for the resource held by the Pn, and finally Pn is waiting for the resource held by P0. So the P0, P1, P2, and Pn minus Pn going to P0, they form a circle. That is the most important characteristic in the deadlock situation. So we can define the deadlock situation using 4 conditions. The mutual exclusion regarding to the resource, only one process can access the resource. And hold and wait, holding at least one resource, then request the other, and no preemption. They don't want to be back up, okay? They don't want to be restart, so it's a greedy start. Keep waiting. And circular wait is a process. They form a circular wait, okay, for hold and wait. So that is the deadlock situation. Then we are going to use to model this deadlock situation and the calculation using the graph. What is a graph?
Collection of many points together.
Graph is data structure. Do not answer all of my question as the data structure. There were students before who answered just data structure, data structure, data structure, data structure. Okay? You need to answer details of that. You may not get the full credit, but it's also a good idea. If you do not know any idea, if you do not have any idea about the question and answer, then please write anything that you know. Okay? Otherwise, even I cannot give the partial point, at least to get the minimum point. But if you leave any question as a blank, it will be automatically 0 point, no credit. But if you write down anything like the data structure, so you may get the minimum point, at least 1. If you are not serious, it doesn't matter. But anyway, try to do your best. But if you know the answer, as simple as possible. You don't have to add a bunch of other things supporting, but think about if you are grading the 50 student, it takes a long time. So do I check all of? So if I can find the keyword or the correct answer, probably you may get the full credit. But if you write a bunch of other things, you may be confused. Okay? Even I'm going to try to my best, fair and the correctness, but when I'm grading the 50, 60 student, maybe possible the wrong, and so if you know the answer, clear and as simple as possible. If you do not know the answer, put anything as much as who knows. Okay, to get the partial credit. That's my suggestion. Anyway, so graph. What is a graph? It's a data structure for what? It has
The collection of so many points.
it's a set of node and set of edges. Node can represent any entity, okay, anything. Then edge can represent the relationship between two nodes, okay. So node can be considered any entity. So because of that, it can represent something relationship between two nodes. We can use such a graph structure for a bunch of other. So especially in the database, we can use such a graph structure a lot. One of the special case of the graph data structure is what? So we can define graph as set of node, vertex, and set of edges. And one of the special types of graph is tree structure. Tree is quite similar as a graph, but it's a set of nodes. Also, it has set of edges, but node has different types of node: root node, internal node, and leaf node. And also, edges is a relationship between two nodes, but it has parent and children relationship. It's a details, specific case of the graph. So tree structure used a lot in computer science. So these can be used. Why? Because it is easy to manage such a specify the relationship like the process. The process create another process. This process create another process. So we can use the tree structure to represent. So this is called the process tree. In the process and resource model, we will adapt idea of graph. Okay, we can use node for what? Process and resource. Okay, and we can use the edges for request or acquire the resource utilization. So first, vertex, the node, we can have the two types of node. One is the process. Okay, specifically we will use the circle to represent the process node. Okay? Then the R is set of resources. At the time we will use rectangle to represent. So for example, in this case, process 1, we have resource 1. We have resource. Okay? Then there are two types of the edges. One is a request edge. It's a request. I'd like to use resource 1. Process 1 would like to use the disk drive 1. This is the request edge. Then if nobody uses this one, so if you acquire the utilization of the resource, you can use acquire assignment edges. So from resource to process. Okay? So this is called resource allocation graph. So we will use such a resource allocation graph to solve the problem of the deadlock. So this slide shows the summary of such a model. Process, so-called resource time. What does that mean? Small rectangle is represent